Chapter 15, Multiple Integrals. So chapter 14, we began by introducing functions of more than one variable, functions of 2 or 3 variables. Then we talked about how to take derivatives of functions of 2 or 3 variables. Of course, we have to be careful about what we mean by taking the derivative, and that's taking partial derivatives. And then the rest of chapter 14 was a variety of applications of partial derivatives. And so now in chapter 15, we're going to be thinking about how to integrate functions of more than one variable. And so chapter 15 is going to be multiple integrals. We'll start off by doing double integrals in sections 15.1 and 15.2. Later on in the chapter, we'll be doing sections that have triple integrals, but we'll start off with double integrals for the time being. So some learning goals here. Know the definition of a double integral as a Riemann sum, understand geometric significance, be able to apply Fubini's theorem, and evaluate iterated integrals. Okay, so let's just do a brief comparison with Calc 1. In Calculus 1, the sorts of integration that we did, let me write down here a sample definite integral. The integral from a to b of f of x dx. The geometric meaning here is area, really we should say signed area under a curve. And so if we draw a picture here, and here is our function f of x, a to b, then this integral here is giving us this signed area. This is the big picture of what it means to have, this is the geometric interpretation of this definite integral here. It's worth noting here that for a formal definition, so how do we formally define a definite integral? We do it using, of course, Riemann sums. So now what we're going to do is that we're going to have double integrals over some region R of some function f of x, y, dA. So what's going on here? So f of x, y, this is a function of 2 variables. dA right here, when we see this little dA, this means a little chunk of area. Just like dx here meant an infinitesimally small chunk of length, this dA here, the differential, is a little chunk of area. And then this r right here, this is the region that we're integrating over. So what I want to do right now is compare this with this right here. I want to get 2 different definitions, 2 different interpretations of this. I want to do the formal definition and the geometric interpretation. The interpretation of this double integral here is going to be signed volume. And signed volume, everything's positive, it's just volume, under a surface but over a region R. So let's draw a picture here. Okay, here is some region R in the xy plane, and we have some surface flowing up here in space, And this surface z is equal to f of xy. So we're defining this surface here through our function of two variables. And so what we're doing is that this double integral here is going to give us the volume under the surface over this region R. So this is the interpretation. A little question here for a formal definition is, again, the answer is going to be through Riemann sums, where the idea is that you, instead of in one variable land, we break up this axis here into little intervals and approximate. Here I'm using left endpoint approximations to approximate it, add up all of those areas, take the limit as the width of the intervals goes to 0. The formal definition here is that we're going to chop up our underlying region R into little squares or little rectangles here, and then for each little rectangle, okay, find the volume of this rectangular prism. Take some test point up here, find the volume of this rectangular prism, and then add up all of the volumes. I drew 1 here, you'd have to do 8 more. Add those up, that gives you an estimate, and then take the limit as everything as those areas go to 0. Okay, so let's do now a pair of examples riffing off of each one of these interpretations, the volume and the formal definition. So let's take a look here at this example. I'm asking us to compute the double integral over R of 3dA, where R is the region in xy plane, xy, such that x squared plus y squared is less than or equal to 1. So this is a circle in the xy plane. Let's get that going on here. So x squared plus y squared is less than or equal to 1. And then the function that we're integrating here, f of xy, is 3. That's a constant. So here is 3. So what's going on here, this double integral is going to be this volume under the surface, z is equal to 3, and over the region R, over the circle, x squared plus y squared is less than or equal to 1. Filled in circle, I should say there. And so why did I choose this example? Nice easy example to get us started here. This is going to be a cylinder. This is going to be a right cylinder, and the volume of the cylinder is going to be height times pi times the radius squared here. And so the height here is 3 times pi times the radius of our circle is 1. So the volume here is 3 pi. So the double integral is equal to 3 pi. Now this is very much a toy example. We're going to, in future videos, do a lot more intricate examples here of how to do them computationally, but because it's so easy, this is just doing it with the geometric interpretation. In terms of Riemann sums here, we're not going to calculate Riemann, do everything with a limit of Riemann sum, but let me just show one example here for an estimate. So let's estimate the double integral of square root x plus square root y dA. For R is the box here, x and y both run from 1 to 3. So the region that we're integrating over is going to be x runs from 1 to 3, y runs from 1 to 3. I didn't tell us how to estimate it, so let's just chop it into 4 boxes. The area of each one of these boxes is going to equal 1. And then we need to approximate, find an approximation for the function f of x, y is square root x plus square root y. Let's pick lower left-hand corners here. That was an arbitrary choice that I just kind of made up on the spot here, but so for each one of these squares, we're going to approximate the function on the square with its with its value at the lower left-hand corner. So right here, f of 1, 1. F of 1, 1 is square root 1 plus square root 1 is equal to 1 plus 1 is 2. Right here, this is f of 2. Oh, sorry, got that backwards. F of 1 comma 2 right here is square root 1 plus square root 2. So that's 1 plus square root 2. Right here, this is f of 2 comma 1 is square root 2 plus 1. And right in here, this is f of 2, 2 is square root 2 plus square root 2. So what we would do then is we would form a, this is, I'm kind of doing this in 3 dimension. Hopefully you can see the point what I'm doing here. Form a rectangular prism here of height 2. Form a rectangular prism here of height square root 2 plus 1. Form a rectangular prism here of height 1 plus square root 2. Form a rectangular prism here of height root 2 plus root 2. And then the volumes are going to be the height times the area, which area is just 1. Area of the base is just 1 here. And so the lower left one, well, let me just kind of do this pictorial. The upper, the top left one is 1 times 1 plus square root 2. The bottom left one is 1 times 2. The top right one is 1 times 2 square root 2. And the bottom right one is 1 times square root 2 plus 1. So what do we do? Add up all of those volumes, and we get 1 plus square root 2 plus 2 square root 2 plus 2 plus square root 2 plus 1. And so our estimate here is 1, 2, 3, 4. 4 plus 4 square root 2. Plop that into the calculator to get a decimal approximation.